Welcome to Reduction of a Ketone Lab. In this video, I'm going to go over gas chromatography, how to calculate corrected percent yield. I'm going to go over some aspects of the NMR related to this lab, and then also we're going to go over stereochemistry, and at the very end of this video, we're going to go through the whole lab in person. A large aspect of this lab is the gas chromatography instrument. We are not actually going to be using this in lab, but we will explain it, and you should be able to do a simple calculation from information given to you from a gas chromatography reading. Essentially, a gas chromatography machine helps us separate and analyze our compounds. With a gas chromatography machine, we can understand how much of our product we actually have compared to contaminants. The capillary column, or what you see here, has something called a stationary phase, which is what it's packed inside with, either a polar or a non-polar surface, and it separates different components according to its polarity, causing them to exit at different times. The mobile phase is what pushes the compound through it, usually something like helium, something that doesn't react with your compound. So going back to this question right here, to how would we get a better resolution on a gas chromatography machine? Well, you could decrease the temperature or decrease the airflow, and that would allow this to be have a higher resolution. Equatorial hydrogens compared to axial hydrogens are more de-shielded or have a higher ppm on an NMR spectrum. Always draw a chair conformation when you have a cyclic compound, like so. So let's talk about corrected percent yield using gas chromatography. Always ignore the first peak, it's air. The peak with the most area under the curve is your product, and we're going to show you an example here in a minute. The way you calculate your corrected percent yield is doing the area of the product over the total area under all of the curves. Multiply this ratio by your percent yield that you calculated before the gas chromatography instrument. Your adjusted percent yield will always be smaller than your original percent yield. It should never be larger. So here's a practice gas chromatography reading. In your reduction of a ketone lab, you got 36% yield. So this is what you calculated at first. You get the following gas chromatogram. What is the corrected percent yield? So here's your retention times. That's what RT stands for. Here's the area under the curve. We're not too worried about the units here because we're just going to get a ratio of the area of our product over the area of all the components. So we're going to assume that the largest area is our product because we're good chemists, and we're going to divide this area by the area of this peak, and this peak as well. These three. We're going to ignore anything below a retention time of 1 because we know that this peak is air, so it's not part of our compound. So we know that because this is the ketone lab, our product is cyclohexanol, and it turned out to have the longest retention time. So think about the stationary phase. Is it going to be a polar or a non-polar stationary phase? Remember, stationary phase is what's filled in the column, the packing, and also remember like dissolves like, or polar attracts polar, and non-polar attracts non-polar. Okay, so here's our HNMR for the product of the reduction of a ketone lab. This is simply a reference molecule. Notice that there's a butyl group when we actually don't have a butyl group on our molecule. This just helps us understand that equatorial hydrogens are more de-shielded compared to axial hydrogens. These values are ppm values that correspond on this axis right here. First, you'll want to draw your product. You'll want to label every hydrogen with letters. The easiest one to label first is going to be your alcohol hydrogen, the one bonded to the oxygen. It's going to be a singlet, and it's going to have an integration of 1. So this signal right here. After that, even though HB is an axial hydrogen, it's right next to an oxygen, which is going to take away its electron density since it's an electronegative atom. And so B will be most deshielded compared to the other hydrogens. Now what's left are the equatorial and the axial hydrogens. Remember that the equatorial ones are more deshielded, and so from the order of being closest to the oxygen to being further away, we're going to start labeling these peaks. So first HF, and then HG, and then HH. All of those are going to be more deshielded than the axial hydrogens. And then we're going to use the same logic to label the axial hydrogens, starting with HC. And you can do that on your own, and you'll have to label HC, HD, and HE. And then don't forget to label your solvents right there and right there. Okay, so this is the CNMR for the same molecule, and this is a 2D NMR plot. It's got the H NMR on the y-axis and the C NMR on the x-axis. And what it shows us is the hydrogen that is directly bonded to a carbon. So we'll start by drawing the molecule, labeling each carbon with numbers, 1 through 4 in this case. And let's just take this example that we were talking about. So this hydrogen is directly bonded to this carbon at 70 ppm, which is right here, which corresponds to carbon 1. It's directly bonded to hydrogen B. And you'll do this for the other carbons. And don't forget to label CdCl3, your solvent. It's a triplet at around 79. Let's talk about diastereotopic and enantiotopic hydrogens. Diastereotopic hydrogens are not equivalent, so they give a different signal in an HNMR. They're usually on the same carbon. Diastereotopic methyl groups are an exception. Think about the environment the hydrogen is in, and always do a deuterium test to verify if they are indeed diastereotopic hydrogens. And we'll do an example here in a little bit. Enantiotopic hydrogens, they are equivalent, so they'll give the same signal in an HNMR. During a deuterium test, they form enantiomers, and they're usually on different carbons. Okay, so let's practice with a simple molecule. We have 3-pentanol. So let's do a deuterium test. Here we have the same molecule drawn out twice. We're going to test for diastereotopic hydrogens. So I'm going to place a deuterium in place of this hydrogen right here, and a deuterium in place of the other hydrogen. And then notice that in the original molecule there are no stereocenters, but once we add a deuterium, we actually create 2 stereos in each molecule. We then label the stereocenters and then compare the molecules to each other. Because only one of the stereocenters changes, they are diastereomers, so therefore the hydrogens we tested with the deuterium are diastereotopic hydrogens. They give a different and unique HNMR signal, even though they're on the same carbon. So now let's test for enantiotopic hydrogens. Same idea, we place a deuterium here in place of this hydrogen and a deuterium here in place of that hydrogen. We created 2 stereocenters on each molecule. We labeled the stereocenters. Notice that this time these are considered enantiomers of each other, so therefore the hydrogens on that we tested as a deuterium, those are considered enantiotopic to each other, meaning they are on different carbons and they are giving the same signal in an HNMR. Okay guys, we're going to start the reduction of a ketone lab. Here's what the apparatus looks like for the beginning. We have a 5 ml conical vial, we have an air condenser, and we have a large spin vane in there. And we're going to add 100 microliters of cyclohexanone. Okay, so we've added the 100 microliters of cyclohexanone. Now we're going to add the 300 microliters of the sodium borohydride reducing agent. We're going to add it dropwise. while spinning. And now we're going to wait 30 to 90 minutes. Okay, so it's been 30 minutes. We're going to stop stirring this. Now we're going to go get the 3 molar hydrochloric acid. So here's the 3 molar hydrochloric acid. We're going to get 1 ml. Cap that back up. Okay, so this will neutralize the reaction so that the sodium borohydride will no longer react. I'll just stir it a little bit. Okay, now we're going to use methylene chloride, our favorite solvent, to separate the cyclohexanol from the water layer. I'm going to put in a little beaker here so it doesn't tip on me. I'm going to take the spin vane out so it doesn't interfere. Here's our methylene chloride. Okay, I'm just going to put a couple milliliters in the conical vial. Get the phases to mix. So you can see the 2 layers, the top being the water layer and the bottom being the organic layer, right where that bubble is. And we want to keep the bottom layer, that's the one with the methylene chloride, that one has our product, the cyclohexanol. We're going to take the bottom layer and put it into the small Erlenmeyer flask. Okay, so we're going to add another little bit of methylene chloride. We're going to do this 3 times to extract as much of the cyclohexanol as we can from the aqueous layer. Then mix this around. Notice the 2 layers are trying to separate. So we're going to put the bottom layer into the 10 ml Erlenmeyer flask. Do that one more time. Let that settle. And then take the bottom layer. Okay, now we're going to use some desiccant. Okay, so here's the sodium sulfate. We're going to use some of this and put it into the Erlenmeyer flask. Just a little bit of this straight into the Erlenmeyer flask. Maybe that will be enough. It's mostly free flowing, so we're going to assume it's enough to dry the solution. Okay, so we're going to transfer this into a conical vial, a clean conical vial. This should be our pure cyclohexanol in methylene chloride. So what we do now is we use a gentle stream of air to evaporate the methylene chloride, and then what will be left is the cyclohexanol. Okay, so we're going to use this final tube to connect it to the lab air, and we're going to turn this on just very gently. We're going to heat this up a little bit so it doesn't get too cold. When you evaporate, it gets really icy, and we don't want it to condense water into the vial. So we're going to keep it here until most of the methylene chloride evaporates, and then we're going to be left with our product. Okay, now we're going to go weigh it. So it's 19.861. So here we have two salt plates. We're going to do a neat IR since we have a liquid product. I'm just going to put about a drop of our product onto one of the salt plates, like that, and then we're going to run it through the IR machine. We're going to collect sample. Perfect. So now we're going to find peaks. And notice that we have a lot of OH. That's our product, cyclohexanol, and a little bit of the carbonyl peak, showing that we have a little bit of contamination from the cyclohexanone.